but it will try to spring back to the resting state, exactly like that.
And I guess, yeah, with very little friction.
Wow.
Hi, I'm Henry Segerman. I'm here with Sabetta Matsumoto, Tim Reinhardt, and Jürgen Richter-Gebert, and we're visiting this huge mathematical artwork. It's called May West.
Yes, May West is in the middle of a roundabout in the middle of Munich, and it's here since about 2011 or so, and it's designed by Los Angeles-based artist Rita McBride.
And obviously we're interested in it because it's an enormous hyperboloid.
So here's a 3D print of a hyperboloid as a smooth surface.
So you may recognize this shape, for instance, from cooling towers of nuclear power plants, or you may have seen it in your multivariate calculus class as the solution of an equation x squared plus y squared equals z squared plus 1.
Less well known is that hyperboloids of one sheet have lines on it. So you can put a stick here and rotate it smoothly around the shape. And you can flip it over to get the second family of lines. The idea of the sculpture is to use these lines to represent the surface.
May West obviously has both families of lines, but why does it also have these circles on it?
Well, here's a smaller version of the thing with wooden skewers and rubber bands. And there are no circles, and well, now it flexes.
Oh, that would be a big problem for a public sculpture, especially one that's running over the tram line.
Yeah, luckily they thought about that.
So actually, as a matter of fact, people have been thinking about these kind of movable models of one-sheeted hyperboloids since quite a while, and actually we are surrounded by some of them here.
Oh, these are fantastic. Jürgen and Tim have taken us to TU Munich, where they've been working on making these types of mathematical models since the 1800s.
Yeah, the space we're currently in is called the X Quadrat. It's a more modern exhibition where we also take school classes, but also kindergarteners or math students. But its roots really lie in the history. So let's have a look at one of the predecessors.
So, we prepared something. So what you see here is a photograph that was taken in 1893, so more than 100 years ago. And this is a model exhibition that took place at Technical University Munich. And if you look here, you see about 110 different models. And among them, there are several hyperboloids if you look closely. And actually there are also nice plaster models, and well, they are kind of famous actually. So we have some of them in the cupboard as well. They are made from the hand of Rudolf Diesel, who was actually the diesel. That diesel, yes.
The same diesel as the fuel?
The same diesel as the fuel. And so when he was in his early 20s, late teens, he was part of a model building club at Technical University Munich. And he was responsible for these ellipsoids and paraboloids and some of the hyperboloids. And they are ingeniously built. So actually, this here is the catalog of this old exhibition. So if you look here, you see it's printed in 1892. So it's a really old thing here. Katalog mathematischer und mathematisch-physikalischer Modelle, Apparate und Instrumente. Sounds impressive, doesn't it? And in here you have, well, plenty of beautiful drawings and nice text. And for instance, this here is the diesel page. Here you see the diesel models. Here you see Diesel's name on it. And actually, one page after that, this is where our story starts. There you have this Professor Olaus Henrici, and he has written, in the year 1873, Professor Henrici asked one of his students to build a model of the hyperboloid of one sheet from thin rods and with threads. So he asked him to put together thin rods and thread them together, and Olaus Henrici was expecting this will get rigid very, very quickly. And the student started to build the model. and came back and said, well, here's the model, but it flexes. It doesn't get rigid. And all of them were surprised, and they were wondering what's going on here. And that's more or less the start of our story, if you want.
And we saw that flexibility in the model of Mae West.
Exactly.
But let's have a look at one of the more historical models now. This is actually built by Hermann Wiener between 1905 and 1912. So it's not the original hyperboloid model that sparked this confusion, but still with this one, you can really nicely see that it has a motion. Do you want to try?
I would love to try. Thank you. Wow. This moves so smoothly. This is an absolutely beautiful model.
And in fact, there exists a photograph of Hermann Wiener showing one of the models to his family, and they are also in awe, or at least they seem to be.
So the model of Mae West obviously flexes. So why would Henrici think it doesn't?
We cannot be certain about that, but we have a suspicion. He could have reasoned along the following lines of thought. Consider a generic three-dimensional object like this stapler here. Then to fix its exact position in space, you require 6 degrees of freedom. That is, you have 3 translational directions, x, y, and z axes, and 3 directions of rotation, like the pitch, the roll, and the yaw of an airplane. Keeping this in mind, let's try to build such a stick model from an hyperboloid all the way up. We will use straws of 2 different colors for that, representing the 2 different rulings, so the 2 families of lines with the different tilts on the hyperboloid. And let's start with 2 of those from the same family, neighboring, moving freely through the air. How many degrees of freedom gives that to us? A single line, to position it in space, you don't get the full 6 degrees of freedom, you only get 5. The reason is that the rotation along the direction of the line, like you see with the stripes, what I do here, this removes 1 degree of freedom because this rotation leaves the line fixed. You can think that the translation would do the same thing, but that is not quite correct because if you add the second ruling, some points on the line will be special and they would move with the translation, but they stay fixed under rotation. Good. So a single line gives us 5 degrees of freedom. Taking another independent second line gives us another 5, 10 degrees of freedom. Okay. Minus the 6 degrees of freedom we need for the general positioning gives us 4 degrees of freedom for the relative positioning of these 2 lines. Now, what happens if we add more lines from the second ruling? We start to build that. If I add 1 more line to this thing, then the distance between 2 points on the lines will have a fixed distance, thus removing 1 degree of freedom. But this thing, by our counting, still has 3 degrees of freedom, and it is pretty much movable almost as I like it. Let's add a second line. So with the second line, the same thing happens. 2 new different points, fixed distance, 1 degree of freedom gets removed, leaving this construction with 2 degrees of freedom, and you can feel how it starts to become more rigid. Let's add a third line. Now, this third line removed, as before, another degree of freedom, leaving this thing with 1 degree of freedom for movement. So let's add the final stick. So after some adjustments, this is now pretty rigid. According to our degree of freedom count, of course, there's some tiny movement due to the material, but feel it for yourself. This is ideally a rigid thing.
Oh, wow. This is quite rigid. So why does the hyperboloid flex? I mean, this argument makes sense and this model is rigid. So why does the hyperboloid flex?
Now it really becomes tricky. So you have this thing here and it really is rigid. It doesn't move. But is it the thing that we want? So we wanted to have two rulings, which means two families of lines. So that means that we should be able to add more lines here. And if I try to add one more line, you see I can touch three of the other lines, but I cannot get it to the fourth line here. And actually, if you create the equation, I give you 4 lines in space and ask you to calculate lines that touch all 4 of them. It turns out that this is a quadratic equation that has exactly 2 solutions. And we see the 2 solutions here, and there are no more. But we want to have more solutions, and to get there, we have to move that in a very special situation. So I have to bring that closer to the other one, and I have to change the positions until they actually meet. And now I'm in a kind of very special position where things are no longer rigid. And there it starts to flex, which is kind of amazing. So generically it's rigid, but in the only case we are interested in, it flexes.
So we moved some rubber bands around, and suddenly our straws became flexible. But that's not really a proof. So can you show me some more math?
Okay. So first of all, historically, the story is kind of involved. So we had Henrici discovering that movement, and then the problem was posted, and then it didn't happen anything for a couple of years. Then the problem was posted in a more prominent context, and Arthur Cayley, who is really a famous British mathematician and a great geometer, came across that problem, and he resolved it completely. So he wrote indeed a 2-page paper doing the most general proof that you can do in this situation. So this here is Cayley's paper. So you see, Cayley was very productive. It's paper number 742. No, 724, sorry. And if you look at it well, you have to do your calculations, and we won't do that here. Let me give you a rough visual idea of what's going on, and for that we really restrict to a special case where we restrict to the circular thing where, you have a circular hole in the middle and everything is nicely aligned, like in the Mae West. So what happens here? So first of all, we have to think, what do we actually want to prove? So that's the first thing in the math statement. What are the definitions? So here you have your sticks and your joints where the sticks come together, and you want to show that this here is a proper motion, what we see in the model. So that means that these distances here remain the same. And so what Cayley actually did, he focused on just 2 sticks essentially, or just only a small number of sticks. So let's take almost all of them out here and just concentrate on 2 sticks here, and that we get a rough reference of where this belongs. You see we have these circles at the top, those ones that we saw in Mae West. Let's keep them in our picture. So what do we have to show? We have to show that under this certain movement, this point here stays in the same distance to the other 2 yellow points when they stay in the same distance. So Cayley considered 2 operations of space. So what he actually considered was, on the one hand, changing the radii of the circles, and on the other hand, moving the circles closer together. Both of them do not preserve the length of the sticks. So if I move that here, sticks get longer or shorter. Same here. But what they preserve is the ratio where this intersection point is with respect to that line. So if it cuts at 2/3 here, it will, no matter what I do here, always cut at 2/3. Okay, so we have these 2 operations, and now we combine them. So if we make the sticks shorter by moving this thing here up, we can make them longer by moving the sticks further out. And so if we combine these 2 motions, which I do now, then the sticks remain in the same length. So we have to combine them in a very controlled way, and there's a formula for doing that, but for now it's okay if we just know there is a way of doing that. And this proportions always stays the same, so the distances stays the same. And now we don't do that just for 2 sticks, we move in all our sticks at the same time, and we could do the same argument for each of these intersections, which proves that in that special case, this thing here is a proper motion.
I see.
So Cayley, in a sense, thinks of this thing in 2 different ways. So on the one hand, it's a mechanical motion. On the other hand, it's a squeezing of the space. So let me show you that squeezing of the space by putting a little object in here. So we have a little rabbit in here. And we now perform our squeeze, and you see really how space gets squeezed, and our poor little rabbit gets, well, squeezed rabbit, and in the other direction it gets stretched. So here you see we have an almost one-dimensional rabbit sitting in here. But for the hyperboloid, which is a special object, it's a nice motion. Strange. I really admire Cayley, and Cayley did something even more complicated. He did that not only for the circular situation, but also for way more general hyperboloids, which we also build.
Cool. So you showed us that I should be able to flatten this all the way down and sort of squeeze it up almost to a straight line. But this one really wants to sort of sit just like this, and I assume that has to do with these rubber bands on
Yes,
it.
exactly. What happens here is that the black rubber bands are attached in a way such that they try to make the sticks perpendicular to each other, because this is closest to the resting state of the rubber band. And having it on every rubber band that way just brings it to that energy optimum here. And if you try to do the movement of the hyperboloid, you work against the rubber bands, against the forces, but it will try to spring back to the resting state exactly like that.
But I remember that the classical models moved a little bit smoother, so how do they work?
Yeah, the classical model has a different mechanism for moving. So if we look at it, there is no intrinsic force that tries to hold it in any position. It just falls down. And the joints of this model explain why this is the case. So if you look closely at those, these joints allow the sticks to rotate against each other, probably best seen for one of these middle joints. But at the same time, the cylinders around each stick allow all the touch points of one stick to rotate around it. So in this way, there are no forces playing, only the pure movability of the thing.
Wow, that's beautiful. But why doesn't it go completely flat? I thought we should be able to make the planar bunny.
We are in the real world here. We are not in. So Cayley's proof was about lines on a hyperboloid, ideal things with no diameter, and here we have real world constraints. So these things have a diameter, they are, well, they are touching, but they are not lines going through each other. So there are boundaries induced by real world constraints. And if you build models, it's something you always have to face. Real world isn't exactly the same thing as the ideal mathematical world, and you have to do compromises, and that was the best compromise in 1905.
So when I collapse this down, it doesn't get completely planar because these sticks have a radius and start crashing together. So what's going on with these models then?
Real life, and let's take real life to the extreme, and we did that here. So now we have real radiuses. Yeah. So and what happens here is, well, if you make it touch here, these things have a finite radius, and they won't touch here. So so as soon as you build that from real sticks, mathematically these things more or less no longer exist. So there are these gaps in between.
Yeah. On the small scale, you can get it to work somehow, but once you start to exaggerate things, the following happens. So the inner tubes, right through their middle, an ideal hyperboloid is running. So that's fine, and the same is also true for the outer ruling. But what we have is two ideal hyperboloids which are not the same. They are offset a lot by the large radii we have here, and what will happen once you go outwards, the hyperboloids diverge. And so at some point, they cannot touch.
I see. So that means there's only a finite number of crossings that can exist on any given model before the model fails.
Exactly.
Exactly, and you see that actually in the May West. So if you look at the May West and look at the different crossings, they are very close together in the middle, and they diverge if you go up or down. And I spoke with the engineer, and they said, well, these were really engineering problems they had to face, and the flexibility was only secondary. These are the real problems. So actually, mathematically, you still want to have a model where these are ideal lines, where they really pass through each other, but somehow reality strikes back, and you have to think of how to create models that become close to mathematics as much as possible.
So trying to get closer to the mathematical ideal is how I got involved in this whole hyperboloids thing, thinking about a different, a way to sort of get around this problem of the sticks can't coincide. So in this model, there are these 3D printed parts around aluminium sticks here. But then the other set of sticks, these green sticks, are actually broken up into lots of separate 3D printed parts. Here's what's going on. We want to have pairs of sticks that intersect at a point, but that can rotate in any way we want relative to that point. Of course, physical sticks don't do this, but we can get the same effect using a bunch of hinge joints. This joint allows for rotation in the plane of the two sticks, and we also have joints allowing the other kinds of rotation. Sabetta figured out how these hinges could be arranged with Eric Vergo, and I implemented the design. To make sure that the distances between joints stay fixed, we added 3D printed sleeves that go around the blue sticks. And to get the largest range of motion, we want this green part to be as long as possible. So we get rid of the green stick entirely and just have 3D printed parts bolted together where the stick used to be. And what that means is that we get very little friction. There's no bending that was happening with the wires or the skewers. And yeah, we get very little friction.
That's fun. May I just feel it?
Yeah.
So what I find amazing, I really know how the classical models feel, and this here is something really different. So the classical models and the rubber band models always resist, and this here is just a smooth mechanism, so you really can speed it up, and I love it. I really love it.
There's a tiny bit of friction maybe with the,
yeah, okay, there's always friction in life. But
I also like, this is a fun thing to do.
Wow.
And I guess, yeah, with very little friction, you can grab it on some sort of symmetrical parts. And of course, it stops at some point because, and you can probably figure out there's bits of plastic that are crashing into each other. So to get it to be truly two-dimensional with a physical model, you need to figure out how to get solid objects to pass through each other, but this is doing pretty well.
Cool.
You said that the mathematically ideal model that Kaylee came up with has a more general case. So can you tell me more about that?
Yes, indeed it has. So let's first have a look what's special in that case. So in that case, you always have this circular cross-section, and you have it at every layer. So the joints here are all on a circle and it flexes nicely circular. And now short proof really applied to that circular case. But Cayley's proof is way more general. And this is even reflected by the classical models. Let's see what we have in our classical collection here. So here you have the stick model and here you have the diesel type model, and all the games we played in the circular case we can also place in that more general case.
Exactly. So for example, in Diesel's model, you can, if you hold it like this, really nicely see how all the cross sections are elliptical. And this elliptical hyperboloid still has two rulings, two families of lines lying on it. And I think this is even more surprising than for the circular case because it looks different if you go around each ellipse.
And as I said, you can do really everything that we did in the other case. Let's take that off here for the moment. So first surprising thing, in the circular case, all the joints always have been coplanar. This is no longer the case here, though. If you look closely, they really go in a curve in space. And now if that happens and you squeeze it together, so one situation will be more or less like we had it. And in the other direction, where the circular one went to an all-line thing, this here is staying kind of two-dimensional. I don't dare to squeeze that model too hard. So let me just take one where I have more confidence in squeezing it. So that's the same thing with our wooden sticks here. And you have this ellipse in the center. And through the entire squeeze, it stays an ellipse, but the ellipse changes its diameter somehow. And if you squeeze it two-dimensional, so in the one extreme case, you really get this nice two-dimensional figure here. We should think for a moment what this means to our bunny. So let's pull out our bunny again, and so have a look at our bunny. So this is the bunny in such a more general case. So you see it still flexes and you can go in one direction and it looks not much different as we had it before, but still the cross section is elliptical here. But if you go in the other direction, it won't turn into a line. It will really turn into this kind of bunny sandwich that we have here, where we really have a proper two-dimensional object with a two-dimensional bunny, not a one-dimensional. Now the natural question is whether we also can build that with our more sophisticated joints, and indeed we can.
Of course we can. So we just did the math and built this big model, and if you put it like this, it lies flat. If you look inside it, you clearly see the ellipse, and due to the joints that are closer to the ideal mathematical case, it moves totally freely. So there are no forces here at all.
Wow.
I love it.
This is so amazing.
How long did it take to build that one?
Many hours. Many hours indeed.
Well, this moves so smoothly.
After looking into all of the mathematics, we'll never look at MoMath the same. As we said, the inner and outer lines have to get further and further away from each other. And you can see that they do. The connectors in the middle are very short and they get much longer further out.
So we got in contact with Steffen Feierabend, who's one of the main construction engineers who was responsible for building that giant structure. And he told us about the many construction challenges that you have to face when you build something like that. And yes, the circles do stabilize that. He called it a kind of shortcut for the forces, but it's not only the motion we were talking about. If you build something of that size, you have to be aware of all kinds of other deformations that may happen, and the circles help also with that respect. So the part below the lower circle is made out of steel and covered with carbon fiber, to look like carbon fiber, whereas the upper part really is carbon fiber, which means that it's relatively light compared to its size. So the sticks up there are 40 meters long, which is approximately 130 feet. People had to care about many things, so they put a model of that in a wind channel to make sure, well, it's stable under wind, but also to make sure that it doesn't make annoying sounds and turns into a giant wind instrument. People had to care about cold weather, so parts of the sculpture are heated to prevent icicles to form and fall down and hurt people. So you see, there were many engineering challenges far beyond what we ever would have imagined.
All right, that's about it for this video. If you'd like to make one of the 3D printed hyperboloids that we've shown in this video, we've got links to all of the files in the description. Also, if you want to make one of these wooden skewers and rubber bands designs, Jürgen has a video with lots of instructions on his channel, so link to that. Jürgen also has a video going into the details of the Cayley proof, so really into the nitty-gritty of the mathematics of that. Thank you to all my Patreon supporters, names on the screen now. Thank you to Tim, Sabetta, and Jürgen for helping with this crazy thing in the middle of a roundabout. Hopefully the audio was good. And finally, thanks for watching. Surely there's a good take in there somewhere.
Yeah.
I think the alarm, the siren coming into shot is just the perfect way to finish this video, right?
Yeah.
Oh.